In this video, we'll talk about polar coordinates. Polar coordinates are a way of identifying the locations of points, just as the Cartesian coordinates, where we use xy coordinates to find the points. In polar coordinates, what we do is find the distance from the origin to that particular point, and we call it r. In this diagram, you can see that this is my origin, and this is the point P that I want to label using polar coordinates. So we calculate the distance from the origin and the point, and we call that r. And similarly, we find the counterclockwise angle from the x-axis. So this is the counterclockwise angle, theta, and this particular angle will give the other coordinate for in the polar coordinates. And these two coordinates seen together, r and theta, will completely define any point uniquely. For instance, if I have a point over here, we start by finding the distance in between these two points. Let's call it r prime, and we also find the angle, let's call it theta prime. So this point will have polar coordinates, r prime, theta prime. And if I want to find the relationship between Cartesian coordinates and the polar coordinates, all we have to do is apply the Pythagorean theorem, which says that since this is the hypotenuse of this particular right triangle, that means r must be equal to the square root, positive square root of x squared plus y squared. Since r is the distance from the origin and the point, r is always positive in any situation. Similarly, using trigonometry on this right triangle, we can find that x is just r cos theta, and y is just r sin theta. Now the polar rectangle is very similar in concepts for the Cartesian rectangle, which you're already familiar with. The rectangle which looks like this, with straight lines, not circular arcs like this one. So here, when we identified the regions, these points were always constant. For instance, if A is a constant, B is a constant, and in the y-axis we have C and D, both are constants. So in Cartesian coordinates, we had, if our bounds were constants like this, we called that our region was rectangular. Now the same concept can be generalized over here, where in this point, the distance between the origin and the points in our region, if they are bounded by two constants a and b, we'll call it a is less than or equal to r is less than, which is less than or equal to b. In other words, all those points have this distance from the origin which must be greater than or equal to a, or less than or equal to b, and the angle of these points must be either, if they're on this line, the angle is alpha. If they're beyond this line, they're greater than alpha, and if they're on this line, then they're smaller than or equal to beta. And anything else will actually lie outside this particular region. For instance, if r is greater than b, it will lie somewhere here. If r is less than a, it will lie somewhere here. If theta is greater than beta, then it will lie somewhere here. If theta is smaller than alpha, it will lie somewhere here. Since the bounds are defined by constants, we call this particular configuration as the polar rectangle. Now, if we want to find the Riemann sum using polar coordinates, we do a very similar thing as we did in the Cartesian case. We divide our total area into smaller sub-rectangles, into small polar rectangles, and we call each of this region with indices I and j, where this particular region is the rij region, and thus this center point is ri star and theta j star, and this particular distance from the origin that this particular arc has is ri minus 1, and what this particular arc has, let's use a different color for this one. This particular arc will have an r value of ri. So in order to find the ijth region, all we need to do is find the particular polar rectangle which should look like this, and it's pretty easy to find this one. So here we can see that r values vary from r minus 1, ri minus 1, which must be smaller than or equal to r, which must be smaller than or equal to Ri. So it cannot exceed this blue line, which means the R value must be smaller than or equal to Ri. And the theta values, since it's within this part, the theta values must also not go beyond these two bounds. So let's write that down. We have theta j minus 1. So theta must be greater than or equal to j minus 1 so that it lies in this region. But it must not exceed theta j, because if it did, then it will lie somewhere along here, which is outside our region of interest. And all these points which have polar coordinates r and theta satisfying these two inequalities will collectively form this area, this region, and this region is we'll call it Rij, the ijth region of this rectangle. Now the midpoint of Rij is easy to find. It's just like finding the midpoint of a line segment, where if it's parallel, let's say if we have an x-axis and it's parallel to the x-axis from A to B, the midpoint is just here with a plus b over 2. The polar rectangle is exactly same. It has like within a radial line, like on a circle. If this is at r equals to a, like let's call this a blue line, and this a red line. This, yeah, let's call this red. We'll have B. So this particular point have an r value which is in between a and b, and since it's lying on the same straight line, it's just a plus b over 2, same radial line, right? So we have an r value of, since we're dealing with I and j, so we have Ri minus 1 plus Ri, the two values for the radius or the distance from the origin, not the radius, it's the distance. So it's divided by 2. Similarly, theta is somewhere in the middle of these two angles. One is true here, the other is true here. This is theta j minus 1 and this is theta j. And the angle in between is also just their addition and addition and then division by 2. So you get theta j minus 1 plus theta j divided by 2. So we also know that the area of a particular circular sector is just half. Let's say if the radius of the circle or the sector is r, then it's half r square. The angles subtended between these two lines let's call this theta. So it's half r square. Theta is the area of this particular red region. So using this, we can also find the area of the small rectangular region. How? We'll first find the area of this larger circular sector, and that is half. It must be Ri. Yeah, it must be Ri, because this line is the distance from the radius to the origin is the Ri actually for this green line. Half r square, and this is delta theta, the difference between these two angles. This is our, so if I zoom in, it will look something like this. The angle will be delta theta, and this will be Ri. Ri will be the radius, so this area will be half Ri squared delta theta. But we have to subtract it from, let's draw this with a red, from this particular sector, so that we only have area of our small polar rectangle in blue. So let's now subtract it. So the smaller region will have a radius of Ri minus 1, this particular line, and this is also Ri minus 1. This is delta theta. The angle does not change even if I change my r value. So the area over here is also half Ri minus 1 squared delta theta. This is the area we're using this to find the area. So now let's simplify this a little bit. We have half and Ri squared minus Ri minus 1 squared delta theta, and this will give us half into Ri minus 1, their differences times their summation, the product and the square of their square subtraction. So it's basically the formula a square minus b square equals to a plus b into a minus b. So but Ri plus Ri minus 1 delta theta. Now note what we can do with this thing is, and yeah, so this thing is our small change in R, right? So we'll call this a small value is Ri minus 1, which we'll call as delta R. So this is delta R, and note what this is. Ri plus Ri minus 1 divided by 2, this thing using this half over here, times delta theta. Now this thing is nothing but our midpoint for this particular polar rectangle. So if this is the radial midpoint, we will then have delta R, R star, delta theta. But we can write this as R star, delta R, delta theta. This is the same thing, just written a different way. And this will come in handy soon. So now what we do is find the Riemann sums because we need to find our double integral, how to evaluate the double integral. So the Riemann sum for Cartesian coordinates is similar. We'll just borrow it from our first lecture in this double integral. So we have this double sum over the function f of x star and y star and delta ai. Notice that there is a I dependence here. Previously all the area of the small segments were equal, but here you can see that the area of each segment increases as we go farther from the radius. This is not the same area as, let's say, this one, or it might decrease as well. But the thing is, it does not stay the same. It changes with angle, and it changes as we move along radially. This area looks bigger than let's say this one. So basically, as we move along I in our sum, our delta I also delta A, or the area, small area of the rectangle, changes. It depends on our indices. So now what we do is simply keep our sum as it is, and f x star y star, since we know that x star is just r star cos theta star, and y star is also r star sin theta star, and delta A, we know that this is r star delta r delta theta. Now what we do is find the double integral. The double integral is the limit where m and n both go to infinity. We know this from our first lecture. So what we do is in this series, the first lecture in this series. So now it's all we need to do is just substitute that in what we just found. Of stars. Now as m and n both go to infinity, our double sum will become a double integral, and this particular function, instead of having star, will only have r, and all the stars will go away. The stars go away with the same reason we discussed in our first lecture, which is that the regions become so narrow that there is no notion of having a center point anymore. So we have now r, the star go away, and these deltas will become d, dr, d theta, And here we go. We have found how to integrate our particular double integral over a region R using polar coordinates. Note that dA is like dr rdr r theta. Previously we had, like for a type 2 region, we had dA equals to dy dx. There was no other factor like an x or y. Here, however, we have dA equals to rdr d theta. In other words, there is an extra factor of r. So this is what we will state as whenever we are dealing with a double integral given in a Cartesian region. Cartesian means that this is given as a function of x and y. So you have to change that first in terms of the polar variable. So we've got r cos theta and then r sin theta, and we bring in the extra r dr d theta. The integration must happen over the region R. The same region, whichever coordinate you use, shouldn't change. Now let's try to geometrically interpret how dA really is r dr d theta. Doesn't look very intuitive, right? However, if you look at this small area, this is an infinitesimal area element. So if we want to find that, we need to find, if we want to find the area of this small rectangle, we need to first find the length of these sides. This is exactly like if we zoom in really large over here, we'll find this particular rectangular shape. And this particular line, since it's so small, this curve really looks like a straight line under the limits of calculus. So this is an angle of delta theta. And if I want to find the arc length, there is a formula for finding the arc length in between two sectors which have a lie on with the same radius. Like if this is some radius, let's say r prime, and this is an angle theta prime, then the arc length, let's call it s prime. S prime is equals to the radius times the angle subtended between these two arcs. So this is just a product of the angle and the radius. This is then r d theta, because the radial distance is r, and this must mean that this r d theta is one side. It's like a side of a rectangle with r d theta, and for the other one we have just dr, because it's a differential element in the direction of the radial line, which is, so it's just going to be dr. Now dA is simply then the length of these two sides. Now usually we do the r integral first, which means we'll write this as r dr d theta instead of r d theta dr. So this is just to ensure that we do the r integral first. So this is a geometrical interpretation of our area element in polar coordinates.